Lesson 3. No, we're doing lesson 4 today, but a review from before the Christmas break. We said for solving circuits, there was 2 rules. We called these Kirchhoff's laws. And the 2 rules, one was for current. The current rule, Alicia, said current in equals current out of any junction. If I have 2 amps coming in this way and 1 amp coming in this way, I got 3 amps coming out. And we used that to look at a bunch of situations. We said, okay, I got 4.5 amps here. If 1 amp went this way, 3.5 amps must have gone that way. Had to. That's the current rule. And that one kids find pretty intuitive. In fact, often they'll just do the math in their heads. They can add and subtract even 1 decimal in their heads. The voltage law was the second one. That was a little more complicated. It said that any voltage that you gain from the battery, this is why I called it the chairlift, you have to lose if you end up back at the bottom of the battery. So let me give you an example. If we look at this circuit here, which I know has drawings all over it, but if I gain 18 volts, I must have lost a total of 18 volts going through those 2 resistors. Had to have. And I must have lost a total of 18 volts going through those 2 resistors, which also implies that these 2 resistors have the same voltage. We're going to dive into that way more. Specifically, we're going to look at series and parallel resistors. But first, I sent you a video just before Christmas about the James Webb Space Telescope. I got up Christmas morning to watch the launch. It was 5 a.m. Santa Claus, watch the James Webb Space Telescope launch. Easy decision. I'm going to watch the James Webb Space Telescope launch because it's pretty cool. And you might recall, and I think somebody, it might have been in this class, asked me, they're parking it at something called the Lagrange point. And I found a really good explanation of what that is, if you want to put your pencils down and look up.
Let's imagine you've been riding along in your spaceship and you just need somewhere to park it because you're going out of town. Where do you put it? You actually don't have that many options. Most places you leave it, it's going to start drifting away. You come back in a few years and it's 1,000,000 miles away.
That's a problem. The best way to explain what a Lagrange point is not to think about gravity as a force, big G, big M, little m over r squared, but you might recall in Physics 11, I showed you, I did a 1-day intro to Einstein's theory of general relativity, which thinks of gravity as curvatures and warps in the fabric of space-time. That's an easier way to think about or understand what a Lagrange point is.
But there are a few excellent parking spots for your ship.
5 of them.
These are called the Lagrange points. The Lagrange points are places where the forces acting on an object are perfectly balanced.
They're places where the curvature of space-time is flat, like a table, which means an object can sit there and stay there. That's a better way to think about it.
Assume we have an object that orbits the sun along with the Earth. We're going to use a rotating coordinate system. This rotates at the same speed as the Earth moves. So, in this coordinate system, the Earth doesn't move.
So we're going to pretend the Earth is at rest and everything is moving around it. You can do that mathematically, okay? It's all relative.
Now, let's look at all the forces that are at work here. To account for the fact that this coordinate system is rotating, we have to add in a centrifugal force that pushes out away from the sun. Then we add in the gravitational force of the sun.
So we're using gravity wells, Einstein's theory of general relativity, as our illustration of how how mass warps and bends the curvature of space-time. So there's the sun's gravity well.
And the gravitational force of the Earth. This
Can you see there's some flat spots? There's a flat spot right about there. There's a Lagrange point. One right about there. One right about there. But these three are really unstable because they're on the peak of a hill. So even though it's flat, if something is a tiny bit off, it's going to start to, I'm going to use air quotes, roll. It's going to be in an unstable gravitational field. It's going to be caught in a gravity well.
This graph shows us the effective potential energy, and it tells us how objects will move. An object whose orbit starts here will slowly drift towards the sun. An object starting here will slowly drift towards the Earth. And an object starting here will slowly drift away into the outer solar system. But an object won't move if the surface is flat. The surface is flat at 5 points, called the Lagrange points. The first 3 points were discovered by Euler. The remaining 2 were discovered by Lagrange.
Yeah.
5 points in all of space, or 5 points between the...
5 points around each orbiting body that orbits the sun, I think.
The last 2 Lagrange points are stable. This means that if an object is slightly off from the point, its orbit will shift slightly, but not too much. The first 3 points are unstable. This means that if an object is just slightly off from the point, it will just move further and further away. Since orbits near the L4, L5 points are stable, objects naturally go there and stay there. All the major planets have their own Lagrange points, and the most massive planet, Jupiter, has thousands of asteroids clustered around its L4 and L5 points. These are called the Trojans. By convention, these asteroids are named after heroes of the Trojan War. The L4 asteroids are named after the Greek warriors, Achilles, Odysseus, Agamemnon. The L5 asteroids are named after the Trojan side, Priam, Paris, etc. NASA has been parking spaceships at Lagrange points for years. There's even room for your spaceship, as long as you can fly it there.
So the James Webb is going to, I don't know if it's L4 or L5, but one of the stable Lagrange points, because then it doesn't need to use a lot of fuel to stay there. It can easily maintain there. The issue with that is they're far enough away that if something goes wrong, we can't repair it. But I don't know if you've been following it. It looks like everything unfolded properly, which was the big worrying part. So all that worked. Is the sun shield unfolded, the antenna unfolded, the telescope, the tripod unfolded. They're kind of reverse engineering origami to do it. Now, as I understand it, it just needs to warm up slowly for a couple of months. They got to bring everything up to temperature for the machinery to run, which just takes a while. Yeah.
Is there the possibility of like running out of space in the Lagrange points, like having too much stuff in the Lagrange points? Like how?
In theory, yes, but they're big.
Okay.
So in the same way, is there the possibility that we'll run out of room for satellites? In theory, yeah. But when you crunch the number, there's a lot of room up there. A lot. As an example, you may have learned that between Jupiter and Mars, there's an asteroid belt. Okay? And you may have seen Star Wars where they're dodging asteroids. That's garbage. NASA regularly sends probes through the asteroid belt. And in theory, could they hit something? Yes, but the probability is so small because it's so big, they don't even work it into their calculations. Whatever. We're good.
They ever hit an asteroid?
Not accidentally. Intentionally, we've sent a couple of probes to run into them. So, back to circuits. We're going to talk about series and parallel circuits. What's a series circuit? A series circuit is where resistors are connected in a row with no junctions in between them. So if I call this circuit 1 and this circuit 2, which of these has resistors in simple series? Okay? Now, what does that mean? It means that, well, first of all, two resistors are in series if there are no junctions between them. Sorry, I should put the answer there, that one, or circle it, or whatever you want to do. This one. What does that mean? If you know that resistors are in series, Kirchhoff's law tells you something about the currents. So example 2 says, analyze the following circuit. Find the voltage drop in each resistor. First, I'm going to label downhill. Downhill is, I guess, this way, because that's which way the current flows. By the way, the electrons flow in the opposite direction, but we decided it was way easier to pretend that protons are moving through the circuit because it's just less confusing. Okay. How many amps are leaving the well, how many amps right here, Kessler? How many amps right here? How many amps right here? How many amps in here? Yep. This was Kirchhoff's rule, Kirchhoff's law for current, 4 amps. Now, do me a favor. At the very, very top of the page, let's write down V equals I times R, that's Ohm's law, and P equals V times I. You have them both on your sheet, but it's worth having those two in your brain. What I said to you before Christmas is if I know 2 things, I know 4 things. So, Kessler, I know 2 things. I know current, I know resistance. What's the voltage drop in R1? I'll call that V1. Sorry? How'd you get that? Okay. How many amps flowing through R2? How many amps right here? 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 So, how many volts through R2? How many volts through R3? Now, there's 2 ways to get it, Deegan. First of all, Deegan, how many amps are going through R3? Yep. And so you could go I times R and get 20, or you could use Kirchhoff's voltage law. Deegan, how many volts are we starting with? How many do I lose going through here? Leaving 36. How many do I lose going through here? Leaving how many? So I can get it 2 ways. I can go I times R, 20, or I can use Kirchhoff's law. The fact that I got the same answer both ways means what? I'm right. Now I could also find power. A follow-up question would be to say, hey, if these are light bulbs, what's the brightest bulb? My mom says I'm not the brightest bulb. She means something different. How do I find power? Oh, well, the easiest one is V times I. 12 times 4, this is a 48 watt bulb. 16 times 4, 64 watt bulb. 20 times 4, 80. Oh, this is the brightest bulb if it was light bulbs. Is that all right? Part B. Can you find a mathematically equivalent resistance if there was only 1 resistor instead of 3? What? In other words, let's do a little quick sketch. Suppose we had a battery, 48 volts, as before, but we only had 1 resistor in the circuit. Now, we're still sending 4 amps from the battery. How many amps are flowing through this mathematically equivalent resistor? How many ohms must this resistor be? How'd you get that? First of all, how many volts do I gain? Everybody? How many volts must I lose? Everybody? And since there's only 1 ski hill, 1 resistor, this must lose 48 volts. Therefore, it would have to be R equals V over I. So this circuit up here is the same as a single resistor. How big? How big is this Anika resistor up here? How big is R1 in ohms? Anybody see how you can mathematically combine resistors in series? Just add them up. That's the easy one, okay? So on the next page, if you want to find R total, it's just R1 plus R2 plus R3 plus R4, however many there are, as long as they're in series and there are no junctions between them. Example 3 says, select the best answer for the voltage drop across the 20 ohm resistor. So here's, you know what, I'm going to call this, let's cleverly go like this. R1 equals 5 ohms and 20 ohm, we'll call that R2. And then I can talk about V2 and I2. Easy peasy. And it says, in R2, is the voltage drop 100 volts, more than 50, less than 50? And convince me. You know what? Let's analyze this circuit. First thing, let's label downhill. Here's the battery. Downhill is from the positive towards the negative. Do I know how many amps are leaving the battery? In fact, do you see amps anywhere? First thing I always look for is current. Then the next thing I look for is there any resistor where I know two pieces of information, where I know two things? I only know one thing there. Only know one thing there. Doesn't help. So, as a last resort, I'll rewrite this as its simplest mathematical equivalent. These two resistors are in series, so instead of a 5 ohm and a 20 ohm, what's that really the same as?
25 ohms.
I can sketch this really quickly, and I'm not even going to do a proper circuitry diagram. Over here in the margin, I'm going to say, look, this is like a 100-volt battery and a 25 ohm resistor. How many volts must be going through that resistor? Okay. How many amps must be going through that resistor? I'll call it I total because that's what's leaving the battery as well. Sorry? This has got to be 100 volts, 4 amps. Now let's walk to our original diagram. How many amps are leaving the battery? 4. How many amps are going through R1? Hey, I know two things. How many volts am I losing through R1? How'd you get that? I times R. V equals I times R. Right? Current times resistance. How many volts do I have left? How many volts do I lose going through here? Now, or I could have said, hey, I also know there's 4 amps here, and I could have gone I times R to get the 80 volts. I don't care which method you use. What's the correct answer, A, B, or C? In R2, in the 20 ohm resistor, are we losing 100 volts, more than 50, or less than 50? It says, explain your answer using principles of physics. Hey, that's what that work there was. Is that okay, Parker? Okay. I may have told you this, but if I haven't, I'll repeat myself anyways. I love solving circuits. I find these like little addictive brain teaser Sudoku puzzles. So you're going to see, I love diving into these things. Okay? Example 4 says, find the total resistance and current, and then find the current through and the voltage drop across each resistor. First thing I'm going to do is label downhill. I will give you a checklist, I think, in the next lesson. But first, were you wondering, how are you doing all this first thing, second thing, third thing? You'll have that as a checklist, but I want you to internalize it first. So label downhill. Second thing I always look for, current. If I can find the total current leaving the battery, the question's going to fall apart. Parker, do you see amps anywhere? Third thing I would try doing, I would try skiing to see if I could somehow figure out a missing voltage. I can't, not going to help me. So, do I have two things anywhere? I asked you that already, sorry. I'm going to rewrite this as its simplest equivalent form. So these 3 resistors are in series. Mathematically, that's the same as a 100-volt battery attached to a single resistor. How big? You only got 20 fingers and toes, so I know, we required you to go an extra 5 there. I guess this must be using up 100 volts. How many amps? How many amps leaving the battery? Even more important, how many amps in the upper resistor? How many amps in the right-hand resistor? How many amps in the bottom resistor? And now for each of these, I know 2 things. I can find the voltage drop in the top resistor, must be 60 volts. Must be 20 volts. And then I could either say 100 minus 60 minus 20 leaves 20, or I could go I times R and say 20 volts. Could I ask you as a follow-up question to find the power use in each resistor? Yeah, either V times I or I squared R or V squared over, I probably use V times I because I have all those. Okay. So that's resistors, Alicia, in series. Parallel is a little trickier. Next page. A parallel circuit is a circuit where the resistors start and end at the same height, same voltage, and then rejoin at the bottom. So if I call this circuit 1, and if I call this circuit 2, which circuit shows resistors in simple parallel? This one. Now, here's what else that means. Let's suppose that this is a 120 volt battery. How many volts am I losing going through this resistor? Did that get me to the bottom? Then I must have lost 120 volts going through that resistor. How many volts am I losing going through this resistor? That got me to the bottom. What about the right-hand one? This is not saying that you're getting 360 volts from a 120 volt battery. You're not. What you're doing is you've got 3 different paths, each path of which is using 120 volts up. And you're draining this battery a lot. Okay? How do we calculate total resistance when they're in parallel? The short answer is we can't. What we can find is its reciprocal. Can you do me a favor? Can all of you get your calculators out if you haven't already? And hold them there. We're going to get to them in just a second. What we can actually find is 1 over R total. And it's 1 over R1 plus 1 over R2 plus 1 over R3 ... And then, once you have that on your calculator, because you've just found 1 over the parallel resistance, the actual parallel resistance is the reciprocal of your answer, of what's sitting on your calculator. You all have a reciprocal button on your calculator. If you want to, you can type 1 divided by 1 divided by 1 divided by. But a much faster way is to use your reciprocal button, which is the little x to the negative 1 button. You all have one. Find it. And we're going to do example 6 together. So example 6 says, find total resistance, total current, and then the current, and heck, for giggles, the voltage running through each resistor. Now, I got to be honest. I don't need to combine these. I have a cheap workaround. Here's what I could do. I could go, how many volts are going through that 10 ohm resistor? I know 2 things. How many volts are going through this 4 ohm resistor? I know 2 things. How many volts are going through this resistor? I know 2 things. So for what it's worth, I do know that it's 36 volts, 36 volts, 36 volts. So this one I don't need to combine, but I did this on purpose to show you that the reciprocal rule is going to work. Here's what we're going to do. We're going to replace this with a single resistor. So we're still going to have a 36-volt battery. But sitting here is going to be one resistor. And what's it going to be? So write this down with me. 1 over R total is going to be 1 over 10 plus 1 over 4 plus 1 over 20. Write that down. And then underneath it or beside it, write R total equals. And now we're going to do the rest on our calculator. I'd like you to follow along with me if you don't mind. So turn your calculator on. Yep.
I can't have my X again, I have a.
Ta-da. Or it might be a 1 over X. You might have a button that says that. Okay? Ready? Instead of, don't write this down, don't type this. Instead of going 1 divided by 10 plus 1 divided, no. 10, hit your reciprocal button. Plus 4, hit your reciprocal button. Plus 20, hit your reciprocal button. Hit equals, and you all have 0.4. That's not the answer. The most common mistake is kids forget this last step. That's the reciprocal of the answer. So now, just hit your reciprocal button again. It should automatically put your answer button there for you. And hit equals. When you combine a 10 ohm, a 4 ohm, and a 20 ohm resistor in parallel, that's the same as a single resistor. How big? What's the current running through here? What's the voltage running through here, Parker? 36 volts. What's the current running through here then? How many amps? 14 point? Even? V over R. Right? Okay. If I know 2 things, I know 4 things. Okay. I'm going to pause for 1 second. R total is 2.5 ohms. Okay. What's I total? How many? Say again, how many? So how many amps are leaving here? 14.4 amps. Now, let's see if we're correct. How many amps are going through the left-hand resistor? Well, that's going to be V divided by R. Logan, please tell me you didn't pick up a calculator to go 3.6 divided by 10. Logan, in your head, without a calculator, 3.6 divided by 10 is what? Sorry, 36 divided by 10 is what? Okay. Yes? How many amps going through this middle resistor? You can do it in your head. What? Yeah? Yeah? 9? Yeah? Yeah? 9? How many amps going through this resistor? You might need a calculator. Let me pause. Are you figuring out, you guys see how we're doing that, right? We're going I equals V over, or we're using V equals I times R and just rearranging it in our heads, right? So, how many amps are going through this right-hand one? Anyone? Sorry? 1.8? When they rejoin, can you add up those currents? Do they add to 14.4? I hope they do. Do they? So this method of combining resistors works. Okay? This method works. Now, I'll be honest. I wouldn't use this method. I would have solved this method by skiing. As soon as I had the voltages, I would have said, oh, 3.6, 9, 1.8. I would have added them to get the 1.4. I wouldn't have walked through. I would not have bothered walking through this bottom step. But sometimes you'll have to. You'll have no choice. You won't have enough information. Example 7. I like example 7. I would consider example 7 a B level question. Okay? It says find R total and I total, and then find V, I, and P for all resistors. Okay. For what it's worth, I can solve this by skiing. Step 1, label downhill. That's downhill, 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 downhill. The reason this question falls apart is I can tell you how many volts I use going in here. How many? Mr. Dewick, how would you give us a question where we couldn't use that? Look up. I would give you one blank resistor right there. And now you don't know how many volts you lost there, so you don't know how many volts you lost there. You can't use that trick, but I'm starting you off a little easier. So I do know this is 60 volts, which means I do know, Logan, in your head without a calculator, can you go figure out the current here? I do know this is 60 volts. Logan, in your head without a calculator, okay? I do know this is 60 volts. And so I can actually tell you I total. Because when they all recombine, how many amps right here? So I could do the second part without having to do anything fancy, but they definitely want me to find R total. Okay, these three resistors are in parallel. I can't find R total. What I can find is 1 over R total. That's going to be 1 over 10 plus 1 over 15 plus 1 over 20. And then R total is going to be the reciprocal of that. This is not going to work out evenly. In fact, I think it's going to be a long, yucky decimal. 10 reciprocal plus 15 reciprocal plus 20 reciprocal. Oh, no, not that. Take the reciprocal. Our total is 4.615384615384615384615384615384. Okay? I'm going to write about 5 sig figs because I'm going to use this. So I'm going to go 4.61538 ohms. Now, I already found I total, but the other way to find I total would be to go voltage total divided by resistance total. Voltage total divided by resistance total. Kiana, what's the total voltage? That's the battery. 60. What's the total resistance? 4.61. I'm going to use my answer button. On your calculator, can you go 60 divided by answer button? What do you get? And exactly, yes? Bang on. So, I found I total. I find R total. I'll put boxes around them. Then it wanted me to find V. Did that already. I did that already. Oh, and P. So power. Whoop. Power is, how do I find power? V times I. Okay, 60 times 6. Logan, in your head without a calculator. How many watts? 360 watts, you say? Very good, Logan. I'm so impressed you're able to do that in your head without a calculator. I can already tell you that's not a light bulb. That's a small appliance. Without any more information. They don't really make 300. They do make 360 watt bulbs probably, but they're not standard. I have a video somewhere. There's a British guy who got a 1 million watt bulb, and it's crazy. Remind me, if we have some free time in these longer classes, I'll try and dig it up. It's crazy. When he first turns it on, it fries his camera. So he has to, whoops, that was stupid in hindsight. Yeah, I guess my camera can't handle 1 million watts of light. Okay. How many watts in the middle resistor? I heard 2,000. I heard 2. What? How are you going to figure that out? I times R, V times I, right? 240. And so a nice follow-up question for this would be, if these are appliances, which one is using the least amount of energy? Well, the one with the lowest wattage, because wattage is how much energy per second. Is that all right? Example 8 is a much better indicator of the kind of question I'm going to expect you to handle. I like example 8. I like example 8. I like example 8. Example 8 is a nice question. It says, find the voltage and power lost in each resistor. Ooh, and find the voltage for the battery. Well, step 1, label downhill. Step 2, try and find total current leaving the battery. Rachel, do I know total current leaving the battery? This question's going to fall apart. I don't know how yet, but trust me, this question's going to fall apart. Rachel, do I know how many amps here and here? No. But then they recombine to 5. Do I know how many amps here and here? Do I know how many amps here and here? Well, because they're identical here and here, I'll bet you it's 2.5 and 2.5. I think I vaguely remember that, but you know what? Let's pretend we don't know that. So even though I know the total current, it hasn't helped me much. Third thing, are there any resistors with 2 things on them? 2 pieces of information. Say no. Can I use the skiing trick? Well, here, since I don't know the voltage of the battery, I don't know how high anything is. I can't ski and figure out any missing voltages. I'm going to have to rewrite this, but I'm going to have to rewrite this very, very specifically. These 2 are in parallel. I'm going to rewrite them as a single resistor. These 2 are in parallel. I'm going to rewrite them as a single resistor. These 2 are in parallel. I'm going to rewrite them as a single resistor. So I'm not going to go 1 over 10 plus 1 over 15 plus 1 over 20 plus 1 over 5 plus 1 over 2, because they're not all in parallel with each other. I'm going to do each little individual pair. I think you have some room up here. We're going to do this one right up here. I'm going to go like this. 1 over our total is 1 over 10 plus 1 over 15. What's that top pair the same as? A single resistor. How big? Is it 6? So down here, Parker, I'm going to start to do a rough sketch. I have mystery battery, 6 ohms. Okay. Over here on the right, I guess it's going to be 1 over R total equals 1 over 20 plus 1 over 5. How big are these 2 resistors if I combine them? Is it 4? So, in my rough sketch, yes? What about the bottom? 1 over R total is going to be 1 over 12 plus 1 over 12. Also 6? Okay. Now what's nice about this, these 3 mathematical equivalents are in series. So I'm going to do one more sketch. If I replace those 3 with one big uber resistor, how big? That whole circuit is the same as a single resistor with 16 ohms. Oh, and Rachel, how many amps are flowing through this single 16 ohm resistor? I know 2 things. Rachel, how many volts are we losing through this mathematically equivalent single resistor? By the way, if you want to multiply by 5, multiply by 10 and divide by 2, if you're trying to do it in your head. How many volts, Rachel? Say it again. How many volts, Rachel? Say it again. I'm repeating it for a reason. How many volts, Rachel? Say it again. How many volts, Rachel? Say it again. So how many volts must this battery be? Gotta be. Let's go label that at the very top. Ha ha! We got one of the answers. Now, It doesn't help me to start skiing yet, but look at this middle drawing. Let's put that 80 on my middle sketch as well. Oh, Rachel, how many amps are going through this 6 ohm mathematical equivalent? How many volts do I lose going through here? Yes? How many volts do I lose going through each one of these? 30 volts. 30 volts. Yeah. Ooh, Rachel, I know 2 things. In your head, without a calculator, how many amps do I lose or am I using in this upper resistor? Yep. How many in the bottom? Now you could either go, well, I got 5 coming in, I got 3 in the top. How many must be in the bottom? 2. Or you could go 30 divided by 15. Do we get the same answer both ways? I think we're right. Ooh, let's go back to my middle drawing. Still 5 amps going through this mathematically equivalent 4 ohm resistor, yes? Hey folks, how many volts do I lose in this right-hand resistor? How many volts do I lose in each of these bad boys? 20 each. Deegan, in your head, how many amps in this resistor right here? How many amps must this one be using, the right-hand one be using then? And you could either go 5, take away 1, or you could have gone 20 divided by 5. Remember I said my prediction for this one was 2.5 and 2.5? Let's see if we can confirm it. Now, how many volts did our battery have to have? 80. Minus 30, 50. Minus 20. This is 30. Or I could have said, hey, it's 5 amps. Yes, it's 30 volts. I can get there both ways. So each of these is 30 volts and 30 volts. It'd be cool if 30 divided by 12 was 2.5, is it? Is it? That's my way of saying type it. Yeah, it is.
Yeah.
Now, the other thing this question said was find the power loss. I'm going to skip that because it's just getting cluttered. Sorry. But for what it's worth, Owen, V times 90 watts up there, 60 watts right there, 20 watts, V times 80 watts. I can figure them all out. Okay. So there's an example of one where you had to rewrite it. In fact, you had to rewrite it twice. And I just do rough sketches. I try and make them fairly big, though, so I can clearly see what's where. Don't do a little small sketch. You're setting yourself up for yuckiness. So, example 8 illustrates an important... built-in error check, first of all. Go back to this picture. Deegan, you might know, I always like to give you a built-in error check, so if you make a typo, you can catch it. Deegan, in these top 2 resistors, what's the smallest resistor out of those 2? Look up. What's the smallest resistor out of those 2? Or you can look on your notes. Yeah, in those top pair, what's the smallest resistor? There's a 15 and there's a 10. What's the smallest resistor out of the 15 and the 10? What's the smallest resistor? 10. I know that when I combine them, our parallel is going to be smaller than the 10. 6. In this right-hand one, Deegan, what's the smallest resistor? I knew the answer was going to be less than 5. In other words, if this had been 1 ohm, I knew this would be less than 1. 12 and 12, I knew the answer was going to be less than 12. So a bit of a built-in error check. If you're combining resistors in parallel, your parallel resistor will always be smaller than the smallest resistor making up the parallels. Other hints, it says on the next page, the voltage drop across parallel resistors is the same as the drop across the equivalent. In other words, 30 volts, 30 volts, 20 volts, 20 volts each, 30 volts, 30 volts each. I said somebody asked about not breakers. What did you ask? Oh, what happens when birds touch either side of a line? I said I'd talk a little bit about how breakers work at least. So in a household circuit, plugs and lights are wired in parallel to 120 volts. It's AC, but a lot of the rules will still work. Each circuit has a circuit breaker that is set to turn itself off automatically when the circuit exceeds a set value, usually 15 amps. When the switch is opened, no more current will flow. Example 9 says this: if we connect a 1200 watt hairdryer and a 500 watt TV to the same circuit, will we trip the breaker? Let's re-sketch this as a circuit diagram. So, instead of a battery, I have an AC source, and the symbol for an AC source is a circle with a little sine wave in it, like that. And then it looks like here's the hairdryer. There's the TV. Okay, Shay, how big is the voltage source? 120. This is alternating current, which means it goes in both directions, but just so we're all thinking the same way, let's pretend downhill is this way. Just so our eyes are all moving in the same direction. What else did they tell me? They told me the power that the hairdryer is using. Shay, what's the power that the hairdryer is using? And the TV? Okay. Let's analyze and solve this circuit. Do I know the total current leaving the battery? It's leaving the, sorry, not a battery, the AC. No. Do we see amps anywhere? Okay. Do I see two things on any resistor anywhere? Let's try skiing. I gain 120 volts. Whee! Oh, how many volts must I lose going through that resistor? Has to be. I know two things. I can tell you the current. In fact, I can even go 1200 divided by 120 in my head without a calculator, I'll bet you. So if power equals V times I guess I equals power divided by V. Yes? So 1200 divided by 120 in your head. The hairdryer is using 10 amps. Yeah, the more amperage, the more heat it's moving around. Okay? Hey, what if I skied this path? How many volts must I be losing in the TV? Got to be 120. How many amps am I using up in the TV? Let's call it 4.2. All right. So how many amps, Shay, right there? How many amps right there? How many amps in this circuit? How many amps can this circuit handle? Will the breaker blow? No. You plug anything else in, it will, right? You're close. You're really close. So we are barely okay. Plug in one more appliance. So this is important. If you do blow a breaker, please do not be the dumb person who resets the breaker, plugs everything back in again, thinking, well, now it'll work. You're demanding more than the circuit can give you, and you cannot argue with the math. Plug it into a different outlet that's on a different circuit. You may find out to your surprise that, oh, these two outlets in the kitchen, it turns out, are on the same circuit. I didn't realize that. I may have told you in the suite where I rent, upstairs in the kitchen and downstairs in my kitchen, these two plugs are on the same circuit. I would love to have my microwave here, but I learned early on, if I was cooking my microwave when they were cooking their microwave, we blew the breaker. And being a good renter, I moved my microwave somewhere else. Can't do anything about it. Can't argue with the physics. What's your homework? Here's what I assigned my block A's. Instead of circling, we're going to skip. I might have assigned them all. I did. I assigned them all. But wait a minute. Here's the good news. You have a fair bit of time. No, this is Tuesday. Yeah, you got till 11:50. You got an hour, just under an hour. 50 minutes to work on this. Okay? So, let's go block C, Mr. Dewick. Homework. Every question.